Okay, good morning. We are going to talk about measures of variability today, and then we're going to talk about a normal distribution or bell-shaped curve and how data containment works in the context of bell-shaped curve, as well as Chebyshev's rule. Okay, measures of variability. What it means is this, how much your data varies from the center. That's what it means. If you have a data set, it may have certain shape or certain structure. So measures of variability, what it tells you is basically how close the data points are or how far apart they are from each other, okay? Again, all of it is with respect to the center or the middle of the data sets. Now, I love to give this example, very simple example, to explain measures of variability, which, by the way, we'll talk about later on, standard deviation, okay? And we are not going to use this expression as much. We are going to talk about standard deviation, okay? And we'll talk about variance a little bit as well. So think of these two data sets, -1, 0, and 1. That's one data set. Obviously, you can see the middle or the center of the data points is 0, average is 0, because -1 plus 0 plus 1 divided by 3 is 0. Then I have a second data set, -100, 0, and 100. If you look at the average for this data set, which is also x bar is equal to 0, and this set also x bar is equal to 0, because -100 -100 plus 0 plus 100 divided by 3 is 0. Now, as a casual observer, what do you see? As a casual observer, what do you see here?
It's the middle number.
Uh-huh. Go ahead.
Just that, like, it's the middle number. It's equaling down to the middle.
Yes, sure. Anything else do you notice here? Any other thing anybody notices?
It's a negative and a positive number, but they're the same number.
Yes, that is also true. Anything else? All of what you're saying is correct, but I kind of am looking for something slightly different. Think of which section are we in. That will give you a clue. One last chance for everybody. Anyone wants to comment? Okay. See, the mean is 0 for this data set, the first one, and the mean is also 0 for the second data set. All right. So look, -1 and +1, if you look at the number line, so let's use number line. So that's your 0. +1 is here, -1 is here. So that's the mean, right? X bar. Now, on the other hand, for the second data set is probably somewhere out here, 100, and out there, -100. Do you see? These two data points are farther out compared to the middle. When we look at the first data set, these two numbers, 1 and -1, they are closer to the mean. Whereas these two numbers, they are far away from the mean. So they are spread farther out with respect to the mean. So that's the observation I kind of wanted you to make. That means these data points are kind of farther apart with respect to the mean, whereas these data points are more closer to the mean. Another way of looking at it, think of this shape. That's not a good drawing. Let me just try to do a slightly better job. I don't think I did any better job. Let's try it again. Maybe third time is the charm. So think of this. This is a bell-shaped curve, but think of another bell-shaped curve. Both of them has the middle right here, X bar. You can see in this one, the data points are more compact or more closer to the mean, whereas in this one, data points are further out with respect to the mean or compared to the mean. Do you see that? That's what the measures of variability is. What it is, it measures the variation in the data set. And the term that we will use is called variance. Okay? Variance is a measure of variability in the data set. Variance is a measure of variability in the data set. But this is a term we will not be using as much. We will take the square root of this value and we will call it standard deviation. And that's the term we'll be using. Standard deviation. Okay, most of the times we will be using this term, and sometimes we will be talking about the variance, which is the square of the standard deviation. So you can think of variance as a square of the standard deviation, or standard deviation is square root of variance, square root of variance. And this is what it means. Remember, when you are talking about variation in data set, in essence, you are talking about how close the data points are with respect to the mean, or how far apart are they with respect to the mean. And remember this example, that'll really help you see things. These two numbers, -1, 0, and 1. Here the variation is less, whereas here the variation is high. Okay. Now this is qualitative discussion that I gave you. Okay, so that you can make sense out of it. But in reality, we are going to actually define it and do it more quantitatively, finding the standard deviation and finding the variance. I gave you qualitative explanation so that you can visualize it, you can understand it. Now, I'm going to give you quantitative explanation, or rather quantitative definition, so that you can quantify it and exactly find it. So let's go ahead and do that. So how do we measure variance? Sample variance. So sample variance is denoted by S square. Population variance is denoted by sigma square. Remember these two things. Like sample mean is denoted by X bar. Population mean is denoted by mu. Similarly, sample variance is denoted by S squared, and population variance is denoted by sigma square. So these two are for sample, and these two are for population. Now, sample standard deviation is denoted by S. Obviously, population standard deviation is denoted by sigma. Sample standard deviation is denoted by S, and population standard deviation is denoted by sigma. Now, how do we define S square or variance? Okay, here is the formula. I'm going to write it out for you. S square is equal to, in the denominator, sample size minus 1. That means n minus 1. N denotes the number of data points in your sample. Like if we consider this sample, we have 4 data points. So my n is going to be 4 here. If I had 4,000 data points, my n is going to be 4,000. Now, what is in the numerator? In the numerator, we have summation I is equal to 1 to n, okay, xi minus x bar, see, x bar, this x bar, whole square. Exact equivalent formula is this one too. In calculations, they use this one more often. S squared is equal to, again, divided by sample size minus 1 and minus 1, summation I is equal to 1 to n x sub I square minus 1 over n times summation I is equal to 1 to n xi, this whole thing squared. And that's what the formula is. Now, let's go ahead and actually do a problem using it. Okay, let's go ahead and do a problem using this thing. First, I'm gonna use so that you can understand how to find standard deviation using this formula. Second, I'm going to use this formula. So I'm going to do it both ways so that you feel comfortable using either of these equations. By the way, in the exam, if I ask you, I'll give you something very simple like this for standard deviation. In reality, you will never ever find standard deviation or variation in the data set. Standard deviation or variation in the data set using these formulas. But you need to understand how these formulas work so that you have a working knowledge of the formula, and then you use some sort of computer software, or even in Excel, you can find standard deviation. So let's use the first formula. First formula, so I'm going to break it down so that you can see what's going on here. I is equal to 1 to n xi minus x bar whole square. That's the formula. Now, what is xi? What is x bar? Remember, we are talking about this data set. What is xi? I mean x bar. X bar is the average, so I'm going to add these numbers: 3 plus -2 plus 0 plus 7, all of it divided by the total number of data points, that is 4. So it's going to be x bar 3 minus 2 is 1 plus 0 is 1 plus 7 is 8. So 8 over 4 is equal to 2. So your x bar is equal to 2. That number doesn't change. Now what is xi? What is xi? Xi is basically, remember, it says I goes from 1 to n. So xi's are going to be x1, x2, x3, and x4. Why do we go up to x4? Because we have 4 data points. If we had 5 data points, we would go up to x5. If we had 6 data points, we would go up to x6, or 7 data points, x7, 8 data points, x8, 9 data points, x9, 10 data points, x10. You get the idea, right? So how far my subscripts are going to go depends on how many data points we have. Now, in our case, we have only 4 data points. So x1 represents the first data point. By the way, ordering doesn't matter here. Okay, so it really is not important. So first data point is x1, which is 3, right? Second data point is -2. Third data point is 0. And the fourth data point is 7. So my x1 is 3, x2 is -1, x3 is 0, x4 is 7. Now, if you were to change the order of this, instead of having it as 3, -2, 0, and 7, you had 7, -2, 0, and 3, then your x1 is going to be this one, x2 is going to be this one, x3 is going to be this one, and x4 is going to be that one. So this doesn't change your answer. Okay, this is not going to make a difference in your final value that you get from the formula. So ordering doesn't matter. So what I'm going to do this. Now that you understand what is x bar and what is xi, let me expand this formula. This is just the top. Okay, this is just the top, and the bottom is you just divided by the sample size minus 1, which is easy. So first I'm going to have xi individual data, then I need x bar, then my objective is to get to this guy. Okay, then I'm gonna find xi minus x bar. That gives me just this middle part without the square. In the next one, I'm going to do xi minus x bar whole square. So whatever is here, right here, in front of the summation, that's what I am looking for. Okay, now what is xi? First data point, x1. So my x1 is gonna be 3. What is my x bar, which is 2? x1 minus 2 is 3 minus 2, which is what? 1. Then I need to square 1. If I square 1, I get 1 square is equal to 1. Now we do the same thing for x2, which is negative 2. What is my x bar? Remember, x bar doesn't change. It's always fixed. What changes is the xi's. So that's still 2. Negative 2 minus 2 is equal to negative 4. Now, this is where people make mistakes. They would do something like this. Negative 4 square is negative 16. This is not what this says. It says you take the whole thing, negative 4, and you square it. So that's going to give you 16. Similarly, x3 is 0, 2. 0 minus 2 is negative 2, and negative 2 whole square is 4. And x4 is 7, and this is 2. 7 minus 2 is equal to 5. 5 square is 25. Now, all you have to do is look at this column and add them up. Why do we add them up? Look, this is because of this summation. You need to add all of them up. So 1 plus 16 is 17, plus 4 is 21. 21 plus 25 is 46. So 46. Now look, this top in the formula is equal to actually 46. So S square,
Beautiful.
S square is equal to this numerator, which is 46, okay, which is 46 divided by
Right.
n minus 1, which is
Beautiful.
4 minus 1, which is 46 over 3. So your S square is 46 over 3. This S square is called variance. This S square is called variance. Now,
Let's go.
how do you get S?
You have to square both sides. The square root.
You have to square root both sides. Exactly. You have to take the square root of both sides. So you take square root of S square is equal to square root of 46 over 3. Square and square root is going to cancel out. That's going to give you S, which is equal to. So now let me use my calculator. See what do I get. 46 divided by 3. 46 divided by 3 is equal to 15.33. Take the square root of it, which is 3.91. 3.9157. Can somebody check it for me, please, if I got it correct? Okay, 46 divided by 3 to the power 0.5. Yeah, it's 3.9157. So that is the standard deviation for this data set. The standard deviation for this data set is 3.9157. All right. Okay. Any question, anybody so far, how to find standard deviation? Great. Now I'm going to do the exact same thing, but this time I'm going to find variance using this one. And then from variance, I take the square root to find standard deviation. So summation xi square. So this is really easy. So this is your xi. You don't even need x bar on this one. And then xi square. So your x1 is 3, x1 square is 9. Your x2 is -2, x2 square whole square, so -2 square is whole square is 4. x3 is 0, so 0 square is also 0. x4 is 5, 5 square is 25. Now look at this part. It is saying summation I is equal to 1 to n xi square. That means you square individual terms and then sum it over, okay, over all the i's. You square individual terms, which we do in this column, then sum it over. That means we have to add this column. So 9 plus 4 is 13 plus 25 is 38, I guess. Yeah, 38. So this is gonna be 38. So I'm gonna put here, this is 38 minus 1 divided by n. N is the sample size. We have 4 data points here, so n is equal to 4. So it's gonna be 4 times summation xi whole square. Summation xi means you need to add all of these guys, okay? If you add all of these guys, sum all the data points, okay? Summation xi, summation I is equal to 1 to n xi. What in essence is saying is that find out x1 plus x2 plus x3 plus x4. That's what it is saying. That means you add the data points x1, x2, x3, x4. So if you add these data points, you're going to get 8. Okay, so this is going to be 8 whole square. All of it divided by n minus 1, meaning 4 minus 1. And now let's go ahead and do the calculations. 38.
That would be 6
Is it 6?
because there's a negative, right?
Or did I make a mistake? Then I made the same mistake in the other one. Oh, sorry. This is 7. Oh, no. So 7. So it's going to be 7 square, not 5 square. 34. So 34 plus 4, 38 plus 9 is 47. This should be 47. Let me just double check to make sure that I didn't make any mistake. 47. Yeah, I think it's 47. This is 47. This is 47. Really? I'm not, you're kidding me. What's wrong with me? Yeah, that's a mistake. 7 square is 49, right?
Yeah.
Okay. 49 plus 59, 58 plus 4 is 62. So 13, 59, 62. So this should be, I'm having addition problem this morning. This is 62 because 7 square is 49, right? All right. So now 3 minus 2 is 1 plus 7 is 8. That's why I get this 8. So let's go ahead and continue with it. So 62 minus 1 over 4 times 64. Do you see that? Because 8 square is 64 divided by 3. Now I'm going to just bring it down here. S squared is equal to 62 minus 4 goes into 64 16 times. So it's going to be 16 divided by 3, or S squared is equal to 64 minus 10 is 50. 62 minus 10 is 52, minus 6 is 46 over 3. If you remember from the last calculation, S square was 46 over 3 in the last calculation as well. So even if I didn't catch this mistake, I would have caught it right here, because my variance wouldn't be the same, and consequently the standard deviation wouldn't be the same. So S square is this. So you take the square root of S square and you take the square root of 46 over 3. Square root is going to cancel. That's going to give you S, which is 3.91, I think 57. See, we got the exact same value for the standard deviation using this formula versus this formula. It really doesn't matter which formula you use, okay? It really doesn't matter which formula you use. You'd always get the same answer. And this formula, this one, is easier, okay? Which is this second one. In computer calculation, in the computing world, they use probably this formula because it's easy to find the square of a number and sum up the numbers, right? So in my opinion, it really doesn't matter which one you use, so long you understand. If you understand both of them, I'm happy for you. Any question, anybody? No questions? All right. Everybody okay before I move on?
Yep.
Okay. Now we are going to talk about distribution of data, but I just realized something. Standard deviation, by the way, one thing about standard deviation, it is never negative. Standard deviation can never be negative. It's either 0 or greater. Because all these things are squared, that's why, okay? Standard deviation can never be negative. It is always 0 or positive. the higher the standard deviation, the more spread out the data points are. Zero deviation means all the numbers are the same kind of, okay? There is no variation in the data set. If you get zero standard deviation, that's an extreme, right? If you have data points like two, bunch of twos in your data set, its standard deviation is going to be zero because all the data points are the same. Now, on the other hand, when the standard deviation is greater than zero or positive, the bigger the number is, the higher the standard deviation is. So a data set with standard deviation of 1 has less variation compared to the another data set, let's say with a standard deviation of 2. That kind of says how closely data points are in one set of data compared to another set. So it gives you an idea, okay? It gives you an idea about the relative closeness of the data points. Okay, all right. Next, a distribution of data. So this is something you may want to remember pretty much for the rest of your life, not even class. This is bell-shaped curve. Also known as normal distribution. Also known as Gaussian distribution. Known as bell-shaped curve, normal distribution, or also known as Gaussian distribution. Depending on who you're talking to, they might use one of these different variations of this. Bell-shaped distribution is something that looks like a bell, like a church bell. If you look at a church bell from the front, this is kind of like the shape you see. So people may call bell curve or normal curve or Gaussian curve. All of these mean this thing. So data, most of the times we would like to have data that is bell-shaped. If you know that your data is bell-shaped, then it's easier to find the properties of that data set, okay? If you know that your data is bell-shaped, it is easier to find the properties of that data set. Now, here is a formula. It's kind of ahead of time. So normally, so this is the symbol we use. I'll try to make it as fancy as I can. If you have a bell-shaped curve with mu, and sometimes they use sigma or sigma square. So mean mu and standard deviation sigma. Standard deviation sigma means variance sigma square. Remember that, okay? If you have a bell-shaped curve with a mean mu and standard deviation sigma, so these are arbitrary values. You can always convert it into something called standard normal distribution. So please remember that. Standard normal distribution. What is standard normal distribution? If you have a normal distribution with a mean of 0 and variance of 1 or standard deviation of 1, we call it standard normal distribution. If you have a data set that has a mean of 0 and standard deviation of 1, it is called standard normal distribution. Now you can always go back and forth between these two. That means you can go from any normal distribution to standard normal distribution or vice versa by using these formulas. This one is for sample. If you're dealing with a sample, and this one is for population, if you're dealing with a population. So you can go back and forth between normal distribution and standard normal distribution. Any questions so far? These formulas are also called z-scores formula. Z-scores formula, which we will be using heavily within a few weeks, within a month or so. We'll start to use it a lot, z-scores formula. So what is it? For sample, z is equal to x minus x bar divided by s. For population, z is equal to x minus mu over sigma. Now, as you can see, your understanding of the difference between S and sigma becomes important, okay? Your understanding of S and sigma is important, the way your understanding of x bar and mu is important. X bar is the mean of the sample. What is a sample? When you collect data, collect a subset, okay? When you collect a subset from the population, it's called sample. Collecting data from that sample is called sampling, okay? Now, when you're talking about the standard deviation of a data set that you got by sampling, sorry, this one, not that one. Standard deviation of a data set that you from which you collected data and you found the standard deviation. If it is a sample from which you collected data and you found the standard deviation, it is called sample standard deviation. And in the case of population, by considering the entire population, the standard deviation that you get is called sigma. Okay, so S stands for sample standard deviation and sigma stands for population standard deviation, and S square is the sample variance and sigma square is population variance. Okay, S is the sample standard deviation, S square is the sample variance, sigma is the population standard deviation, sigma square is the population variance. And these two formulas are useful, but in reality, we'll probably be using this one profusely. Okay, let's put it that way. Now, let's talk about this example. An online survey of 164 undergraduates at Baylor University found that they spent the most time texting with an average of 94.6 minutes a day. That's a lot of time for texting. That was followed by sending emails, which is 48.5, and checking Facebook, 38, all of these things. You can read it up. Miss Popular undergraduate spends about 150 minutes per day texting. Given that standard deviation for the texting time per day is 25 minutes, what is her z-scores? When I say z-score, I kind of implicitly assume that the distribution or shape of the data or structure of the data that you're dealing with is bell-shaped, okay? Would she be considered an outlier? Now, remember, our formula is this guy, z-scores formula. Z is equal to x minus x bar divided by the standard deviation. X is the data point in question. In our case, the data point in question is Miss Popular undergraduates number of minutes on that texting, which is 150 minutes. Minus x bar is the average for the sample in this case, which is 94.6, 94.6. All of it divided by the sample standard deviation, which is 25 minutes. So 25. So 150 minus 94.6, there's gonna be 55.4. Okay, all of it divided by 25. So let me do the math for you. 150 minus 94.5, sorry, 94.6 is 55.4 divided by 25, which gives me 2.216. 2.216. So your Z scores for this is 2.216. So this is just one example. So that gives you this. Now, would she be considered an outlier? Now, for that, I have to kind of give you a little bit of new information. What is an outlier? An outlier is a data point, okay? An outlier is a data point that has a Z-score, okay? Z-score greater than or equal to 2, or Z-score less than equal to -2. Another way of saying the same thing is -2 is less than equal to Z. Z stands for Z-score is, oops, okay, not this, sorry, I meant to say the other way. Z is less than equal to -2, or Z is greater than equal to +2. If that happens, that data point is considered an outlier. So for Miss Popular Undergraduate, she spends 150 minutes on the phone texting her Z-score or standardized score. Also, when they say Z-score, they may use different terms, standardized score, okay? So her Z-score is 2.216, which is obviously greater than 2, so she would be considered an outlier. Outlier is an extreme data point. It could be very large or very small compared to the data points in the data set, okay? Outlier is an extreme data point, meaning it could be very big or very small compared to the data that you're considering. Any question, anybody? All right. Next question is this. Let's say Miss Shy or Mr. Shy, doesn't matter. Okay, whatever you put. Miss/Mr. Shy. At Baylor University spends, let's say, let's say, 20 minutes texting every day. Okay, 20 minutes. Now, would that be considered an outlier? So let's try it. Z is gonna be X minus X bar divided by S. X is the data point in question, which is 20, minus X bar is the average number of minutes that people or students use texting, which is 90.6, divided by the standard deviation, which is 25. So Z is gonna be -70.6 divided by 25. So 70.6 divided by 25, which is gonna give me Z is equal to -2.824. Yes, somebody had a question?
Wouldn't it be 94.6?
Oh, is it 94? Oh, sorry, thank you. 94.6. So that's gonna make it even worse. 74.6, right? So 74.6 divided by 25, which is 2.984. So 2.984. Now, would this person, Miss Shy or Mr. Shy, would be considered an outlier? The answer is yes, because this number is less than what? Less than or equal to -2.00. So when Z score is greater than 2.0, So z scores or z is greater than or equal to 2.0 or z is less than or equal to -2, then what happens is that that data point is considered an outlier. Outlier is a general term. It means could be very big or very small compared to other data points. Now, are you comfortable with this, everybody? Everybody?
Yes.
Yes.
Okay. All right, so let's go ahead and start working on things. Now, we are going to talk about something called empirical rule. All right, empirical rule. When you have a data set that is bell-shaped, okay, when you have a data set that is bell-shaped, that you can make some assumptions about the containment of the data, about how data points are distributed, okay? So let's say this is a bell shape with a mean x bar is equal to 0. This is a data set that is bell shaped with a mean x bar is equal to 0 and standard deviation s is equal to 1. Okay, x bar is equal to 0. So this is a normal distribution with a mean of 0 and a standard deviation of 1, which, by the way, is also known as standard normal distribution. You could have normal distribution with mean of 5 and standard deviation of 6. Or you could have normal distribution with mean of -10 and standard deviation of 2, right? All of these arbitrary normal distributions, you can take them and convert it into standard normal distribution, which is a mean of 0 and standard deviation of 1, which has a mean of 0 and standard deviation of 1. All right. Now, if you start at the mean and move one standard deviation to the right, since standard deviation is 1, you will get to 1. If you move one standard deviation to the left, you're going to get to -1. If you move one standard deviation from the center of the data point, which is mean, in this case 0, right? And move one standard deviation to the left, in between these, you include about 68.2% of the total data. That's this blue region. Okay. Now, instead of moving one standard deviation, if you move two standard deviations, that means you go to 2 to the right and 2 to the left, you'll be including 95% of the data points. For bell-shaped, it has to be bell-shaped. So that means you're talking about this blue portion and these purple portions to the right. Now, if you break it down, you'll see this purple portion is going to be 13.6% or around there, about 13.6%. If you add these numbers up, it kind of comes out to roughly about 95%. Now, instead of going 2 standard deviations to the right, if you go 3 standard deviations to the right and 3 to the left, then you'd be including blue portion, purple portions, plus this yellow little tails. That includes 99.7% of the total data. So if you move 3 standard deviations to the right and 3 standard deviations to the left, from the center or mean of the data points, you include roughly about 99.7% of the data. This is called empirical rule. The name comes from the fact that it's based on experience, based on dealing with data sets that has bell-shaped, okay? Based on dealing with data sets that has bell-shaped. So this is called empirical rule. The word empirical means you learn from experience. That's what it is. So empirical rule applies only to data set that has bell-shaped or normal distribution, or also known as Gaussian distribution. It does not apply to other distributions or other shapes. Only this shape you can apply empirical rule. Remember, once again, to summarize, if you move one standard deviation, to the right and one to the left, is going to be 68.2% approximately. If you move 2 to the right and 2 to the left, it's approximately 95% of the total data. Is going to contain approximately 95% of the total data. If you move 3 to the right and 3 to the left, is going to approximately contain 99.7% of the total data points. So it's an approximation. Now we should be ready to do these problems. I have been getting a lot of emails from people about how do I do this problem, okay? So now you have the tools to do this problem. We are going to be using the empirical rules. So let's just leave it here. You take a random sample of 200 people from Salinas and find that their average income is 48,000, okay, per year with standard deviation of 9,000. Also assume that income from Salinas is normally distributed, and we exclude the outliers, okay? Oops. Exclude outliers. What does that mean? If you surveyed 200 people and out of 200 people, you found one person or two persons who make more than $1 million, they might kind of change the average. So you kind of kick them out. Remember, I said for income, we use median instead of average. Even though I have used average here, I just like to talk about average income. Median sounds a bit kind of, I don't know. It's a personal preference. Even though technically you should be using this median, okay? For home prices, for salaries or incomes, they talk about median income. But I'm saying that we are excluding outliers or extreme data points, so we are okay. We can use the mean here. So you took a sample of 200 people and found that their average is $48,000 per year, and standard deviation of the data set, simple standard deviation, or S. Remember, this is going to be your S, and this is going to be your X bar, because you took a sample and your sample size N is equal to 200. So now, what can you say about the number of people who make more than $57,000 per year? So remember, assume that income from Salinas is normally distributed, meaning bell-shaped. So to answer these questions, first thing you want to do is draw a bell-shaped curve and label things. Your mean is 48K, right? And standard deviation, so that's your X bar. Standard deviation is 9K or 9,000. So to get to $57,000 per year, 57, so 48 is right here in the middle, 57. If you move one standard deviation to the right, 48 plus 9 is 57. So that's your 57K. So now you draw a vertical line. You want to find out more than 57,000. So you're looking for this region. And that's how you want to do these problems. Shade the appropriate region after creating the diagram, and then try to find out what this region is going to be. Now I'm going to throw the question back to you. I know many of you have tried this problem. Can you please tell me what's up with this? What is it going to be? Approximately how many people make more than 57,000? Anybody wants to take a chance? Anybody? Nobody? Nobody wants to try it? Okay. Now let's use a different color so that you can see it better. First of all, how far are you moving to the right? 1 standard deviation. What if you also moved 1 standard deviation to the left? That would be 48 minus 9, which is 39, okay? Then what percentage of the data would you include between these two green points? Can you tell me that? It is gonna be 68.2%. Why? You moved 1 standard deviation to the right and 1 to the left. So this middle portion is gonna be 68.2%. 68.2%. Okay. Now, what is gonna be outside? If the middle is 68.2%, what is outside? Meaning, what is here and what is here? Remember, all the data together is gonna have to add up to what? 100%. So if this middle is 68.2%, what is outside? To the right and to the left is gonna be 100% minus 68.2%, which is gonna give you what? 31.8%, I guess. Is that right? Okay, hold on. 100 minus 68.2 is what happened? 100 minus 68.2, 31.8%. Okay. Now that 31.8% has to be divided into 2 regions. Half of it is going to be to the right and half of it is going to be to the left. Half of 38, so take this number and divide it by 2, that's going to give you 15.9%. So this is going to be 15.9%, and this left side is going to be 15.9%. So approximately this region, or people who make more than $57,000 per year, would be about 15.9% of the total data you collected. So it's going to be 15.9% of 200. So 15.9% is 15.9 over 100 of means multiplication or times of 200. 100 goes into 200 2 times. So there's going to be 31.8, 2 times 15.9, or approximately 32 people. So your answer should be approximately 32 people in the sample make more than 58,000 per year. And that's how you do this problem. Approximately 32 people in the sample make more than 58,000 per year. Is everybody okay with it?
I'm not sure I understand why it's 32 and not 15.9, because we're asking for the positive, not the negative. Isn't the 32 combining both the positive and the negative side? Or
No.
population? No. Okay.
No. Okay, let me see. See, I said approximately how many people make more than 57,000? So how many people out of 200 that makes more than 57,000. So it happens to be that I'm multiplying it by 2. What if I had 500 people, okay? Or 1,000 people, let's say. So it's going to be 15.9% of 1,000, right? In that case, it's going to be 15.9 divided by 100 times 1,000. This goes into this 10 times. So you're going to multiply 15.9 by 10. It's going to be 159 people.
Okay, I understand now. Thank you.
Is this question clear to everybody?
Yes.
Okay. Good. Now that leads to the next question. Approximately how many people make between 39,000 and 66,000? So you wanna, again, draw a bell-shaped curve like that. This is your X bar, 48K, right? Standard deviation S is 9K or 9,000, right? Now, you kind of have to draw diagrams. That's something that's going to help you. So let's look at this. Our lower point is 39,000. So to go from 48,000 to, let's say, 39,000 here, right? How many standard deviations you have to move? Just one. Because 48K minus 9K is 39K. So you're moving to the left, one standard deviation. You're moving to the left, one standard deviation. Now, to get to 66K from the mean, which is 48,000, how many standard deviations you have to move? So 48K plus 9K, that's going to give me 57K, right? Then from 57K, I add another 9K to get to 66K. So we are moving one standard deviation plus another standard deviation, two standard deviations to the right. So one standard deviation is going to take you to 57K, and two standard deviation is going to take you to 66K. Okay? Now, the problem is asking approximately how many people fall in this window? Approximately how many people fall in this window? Or how many people make between 39K and 66K? Now, to solve this problem, anybody has any suggestion? Now that you have seen one example, this should make a bit more sense to you. Okay. So first thing, what if you moved just one standard deviations to the left and one to the right? That means this would be this. That we know is going to be 68.2% of the data. Now, we just need to find this blue shaded region somehow. What if, so to find the blue shaded region, we kind of have to consider, what if we moved 2 to the right and 2 to the left? Instead of 39, we go 1 down, 39 minus 9, which is going to be 30K, right? If we move 2, then we will have also this guy too, this 2 blue shaded region. Now, look, if you move 2 to the right to 66 and 2 to the left to 30, you will be including 95% of the total data. That's what empirical rule tells you. But this green shaded region in the middle is 68%, 68.2%. So you subtract 68.2%. So 95 minus 68.2 is 26.8%. But that 26.8% has to be divided into two, right? Half of it is going to be this little green portion, a blue portion. Half of it is going to be this little blue portion. So if you divide it by 2, that's going to give you 13.4%. So this is going to be 13.4%, and this is going to be 13.4%. Now, the left side, we are not interested in. We don't care about it. That's not my interest. But the right side, we want it, because we are trying to go from 39 to 66. Now, the green portion is 68.2%. We know the green portion, 68 middle, you move one standard deviation to the right and one to the left, 68.2%. Plus, you have to add this portion, which is 13.4%, 13.4%. So 68.2 plus 13.4%, 81.6%, 81.6%. So approximately 81.6% of the people or the sample make between 39,000 and 66,000. Between 39,000 and 66,000. Okay, so that's what it is. Now, but 81.6% of the total people you sample, which is 200. So that's going to be 81.6 over 100 of means times 200. That's 2. 81, 162, 163.2. 163.2, because 2 times 81.6 is 163.2, or approximately, people cannot be fractions, right? So approximately 164 people make between what was the number, 39K and 66K. And that's what you should be thinking. Approximately 164 people make between 39K and 66K. Is this okay, everybody? Any question, anybody?
Yes.
Yes, what is the question?
Oh, no, I meant yes, it's okay. I understand.
Okay. Anybody? So this should be one of the questions that I ask you in the homework. Now that I went over an example, you should be able to answer that question very easily. If you get stuck, watch the video again, this portion, which I'm recording and I'll be sending it to you. I think it's time to take a little break. So it's 9:50, so we'll meet at after the break. Oh, hold on. And okay, admit. Now we're going to talk about Chebyshev's rule. Chebyshev's rule is another rule like empirical rule for data containment. Empirical rule, it applies to bell-shaped curve or normal distribution or Gaussian distribution. However, Chebyshev's rule applies to any shape of data. Okay? So if you don't know that your data is bell-shaped, in that case, you can use Chebyshev's rule. But if you do know that your data is bell-shaped or normal or Gaussian, in that case, you can go ahead and use the empirical rule. Now, what does Chebyshev's rule tell you? Let's assume that k is a number greater than 1, okay? what Chebyshev's rule says that if you move k standard deviations to the right and k standard deviations to the left, you contain at least this much data, 1 minus 1 over k square % of data. Okay, 1 minus 1 over k square, which will be a fraction, by the way, right? K is greater than 1 is going to be a fraction between 0 and 1. It's never going to be 0 in theory, right? But it's going to be a number between 0 and 1. Now, having said that, Chebyshev's rule applies to arbitrary distribution. That means we are not talking about bell-shaped curve. And also another feature of another keyword in Chebyshev's rule is this. It is at least as opposed to approximately. At least this much data is contained, as opposed to here, we used the word approximately, okay? Now, let's assume that you take a random sample of 200 people from Salinas and find that their average income is 48,000 per year with standard deviation 9,000. Exactly the same problem as the last one, except this time I don't tell you that it's bell-shaped. So you don't know whether it's normal. So you cannot assume unless you have knowledge or you're given explicitly that the data you're dealing with is bell-shaped. So in this case, it is not bell-shaped. It could be something else. What can you say about the number of people who make between 25,500 and 70,500? Okay. Now remember, K is the number of standard deviations that you move to the right or to the left. So let's say this is the distribution. I'm just making it up, something like this. And your mean is, let's say, somewhere here, 48K, that's your X bar, and S is 9K. Now we are trying to find what can you say about the number of people who make between 25.5K, right? 25,500 and 1,500 or 70.5K. So what can you say about the data containment between these 2 points? This point and this point. What can you say that? Now, since we do not know that it is bell-shaped, we must have to use Chebyshev's rule. Chebyshev's rule tells you the data containment would be 1 minus 1 over k square %. Okay. If you want to actually get the actual percentage, this is going to be a decimal. You can multiply it by 100. All right. But let's just leave it there right now. 1 minus 1 over k square. Now, if you start off at 48,000, how many standard deviations would it take you to get to 25,500? The easy way to do it is kind of like use the z-scores formula, but instead of z, we are going to use the k. X minus x bar divided by s. So my k value is going to be, x is the point in question, which is 25,500, minus x bar is the average, which is 48,000, all of it divided by standard deviation of the sample, which is 9,000, or k is equal to, so 48,000, so oops, 8,100. So this is gonna be negative 22,500 divided by 9,000. So that's gonna give you K is equal to negative 2.5. So you're gonna move 2.5 standard deviations, 2.5 S or 2.5 standard deviations to the left. Now, how much do you move to the right? You can check it in exactly the same way. You will see that it's 2.5 to the right. So it's going to be K is equal to 70,500 minus 48,000 divided by 9,000 standard deviation. That's going to give you K is equal to 22,500 divided by 9,000, or K is equal to 2.5. Okay, K is 2.5. So you're moving 2.5 standard deviations to the right and 2.5 standard deviations to the left, the same value you're going. So your K you found out is actually 2.5. You can think of that way. So now this is going to be 1 minus 1 over 2.5 whole square, which is 1 minus 1 over 6.25. So if you simplify it, 1 divided by 6.25 minus 1, so that's 0.84. So 0.84. Remember, I told you you could multiply it by 100 to get the actual percentage. So that tells you 0.84 is 84%, right? So at least, so remember this keyword, at least 84% of 200 people make between what? 70,000, 25,500 and 70,500. So 84% means 84 of 100 of means times 200. 100 goes into 200 2 times. 2 times 84 is 168. So at least 168 people make between 25.5K and 70.5K. That's what it is. So that's how you do this problem. When you do not know what your distribution is, or what is the shape of your data set is, in that case, you are going to be using Chebyshev's rule. That's what it is. And the Chebyshev's rule gives you this percentage of the data, 1 minus 1 over 1 minus K square. Okay, that's going to give you the percentage of data that is contained within the point of interest. In our case, we moved 2.5 standard deviations to the right and 2.5 standard deviations to the left. So our K was 2.5. We plug in that value right here in the formula. If we simplify the calculations, we get 0.84, which is the same as saying 84%, okay? 84% of the people that you collected data from makes at least 25.5 thousand and 70.5 thousand in between those two numbers. So your final conclusion, you have to say at least as opposed to approximately for bell-shaped, okay? At least 168 people make between 25,500 and 70,500. So that's how you do this problem. Now, anybody has any question on this? Anyone has any question? Okay. Next question is this. What can you say about the number of people who make more than 70,500? It's exactly the same problem like the last one. So let me just sketch it again. So this is the distribution. All I'm saying that this is arbitrary distribution. We don't know. That's what it is. X bar, and which is 48K. And this is 70,500 or 70.5K. So this time, I don't want in between. I want 70.5 thousand. So that means I'm looking for this one. In the last one, I was looking for this. So this is 25.5K. So last time, I was looking for this green shaded region. Remember that. This time, I'm looking for the blue shaded region. Because last time the question was, what can you say about the number of people who make between these two numbers, 25,500 and 70,500, which would be this. Now, what can you say about the number of people who make more than 70,500? So I am interested in this blue shaded region to the right. Just to remind you, we know that at least 84% fall between these. At least 84% fall between 25.5 thousand and 70.5 thousand. Now, what can you say about the data that fall outside of or to the right of 70,500 or more people who make more than 70,500? This question is slightly tricky. So I want you to think about it a little bit. So go ahead and think about it, everybody, a little bit. I'll give you 30 seconds to think about, and I want a response from you guys. Anybody, any response? No one has any response to it?
Would it be the remaining people out of the 200 would fall in the make more than 70,500K?
So remaining people, what? How many or what percentage?
So it would be the 32 people left to complete the 200 people?
Okay, which is like 16%, right? You were saying 16%.
Correct.
So 16%. Okay, good. That's a good start, Alicia. Anybody else has anything?
I was thinking 8%, but I'm not sure.
Okay, you're thinking, Brandy, 8%. Okay, anybody else has any other thoughts? No one has any other thoughts? Okay. The response to this question is kind of interesting. Remember, last time we said at least 84% fall in the middle, right? So at least 84% means 84% of 200, at least 168. So at least 168 falls here. Now, what does this statement or the qualifier at least mean? It could be 168. What if there are 169 people in the middle? Is this statement still true?
Yes, because you're using the word at least.
Yes. Thank you, Alicia. What about 170? Is it still true?
Yes.
What about 200? Is it still true?
Yes, basically everything over 168.
Exactly. So it could be anything over 168 that could be within these two, because it says at least 168. So if 168 or more of them are in the middle, what could be outside, to the right and also to the left? The outside could be what? At most. So see, the lowest the middle could have is 168 people. But what if 200 people are in the middle? Then what is outside? 0, isn't it?
Yes.
What if all 200? What if 199 people are in the middle? What is outside? 1. What is 198 people are in the middle? What is outside? 2. And dot, dot, dot. What is 170 people are in the middle? What is outside? 30. What if 169 people are in the middle? What is outside? 31. What if 168 people are in the middle? What is outside? 32. Can you have more than 32 outside on the outside?
No.
No.
No, because it says, yes, that's correct. Thank you. Because it says in the middle, we have to have at least 168, according to Chebyshev's rule. At least 168, meaning it cannot be less than 168. So that means outside, it cannot be more than 32. It could be 32, 31, 30, or all the way down to, it could be what? 0.
No.
So that's one way of thinking. Then another question I think Brandy brought up, she said 8% on the right, 8% on the left. That does not apply here. Sometimes people think, okay, 84% in the middle, remaining 100 minus 84, 16%. 16%, half of it is going to be to the right, half of it is going to be to the left. You are making the assumption that they are symmetric, meaning left is a mirror image of the right, which is true only if it is bell-shaped. But we don't know that it is bell-shaped. So we really cannot say that half of possible up to 32 possible wage earners would fall either to the right and to the left. You cannot say half is going to go to the right and other half is going to go to the left. You don't know. Since there is no symmetry, since there is no mirror imaging going on here, it could be the case, let's say in the middle there is actually 168, then it is possible that all of 32 is to the right, or it is even possible that all of this 32 is in the left. Also, it is possible that maybe half is to the right, half is to the left, or it's possible that there are 2 in the right and 30 in the left. We do not know for sure. So our best response to this question would be, at most 32 people make more than $70,500 per year. At most. Now, this is critical. At most, meaning it could be up to 32, or it could be as low as what? 0. This is kind of like sales ad. That's what it is. They would write they don't write at most first. They would write 70% off up to. Do you see that? This kind of ads, 70% off. So not so sophisticated buyers, they would look, hey, 70% off, let's go to the store. But it says up to. That means it could be anything 70% or less. It could be as low as 0. So by putting this type of ads, they are trying to get your attention and get you to the store or their website, whatever it is. The thing that they're selling for 70%, you probably even don't want it, likely, more than likely. The things that you want, those may not be at 70% discount. So there are so many tricky business in the sales. It's kind of interesting. Now, in this particular problem, you cannot say this at least qualifier kind of creates the opposite situation or complementary situation, which is at most. So it could be 32 on the right, it could be 31 all the way down to down to 0. That's what it is. Is it okay, guys? Is it making sense?
Yes.
Yes.
Yeah.
Great. So that kind of concludes this topic. Next, we are going to talk about probability. I don't think I'm going to start it today. I don't want to overwhelm you guys with lots of information, but I will be sending this handout. I don't think I did send the handout. I'll be sending this handout to you guys. And we are going to be working on it on Wednesday. And looks like next Monday is a holiday. So no class on Monday, next Monday, a week from today. It's President's Day or something. Okay, so any question about the materials that I covered today? Okay, I'll send you the lecture notes for next lecture, which is Wednesday, and you should receive it in your email shortly by the end of day today. And now you are ready to do all the homework. If you have any questions on the homework, bring them to the class on Wednesday. I'll do them for you. Okay. If there is any particular problem that you are struggling with, in particular, empirical rule and Chebyshev's rule, if you're struggling with those, let me know. It's exactly the same. I just changed the numbers. Okay. What you see on the website is exactly same problem. I just switched the numbers. I increased it to like 500 or something instead of 200. So if you understood what I did, should be pretty clear. Okay, that's all for today. Thank you so very much. You guys have a wonderful day.
Thank
You
you.
too. Thank you.
Yeah.